Assalamu alaikum. This is our final snake ladder game presented by Team What Wizards. So in this video, all the modules have been gathered over here. So we will try to go through each of these modules in short, and later on we will describe each of these modules further. So this is our dice subcircuit of our dice module. So this dice module works whenever we roll the dice over here. For example, wait. If we roll the dice over here, we can see the output display of the dice module changes like this. Okay, the output display of the dice module is changing, and when we are selecting the players, then the position of the players will be changed in the board module. So let's describe this board module first. So what does this board module does? So there are 64 LEDs connected in this board module. There are 16 blocks over here. Each of these blocks has 4 LED. The red LED represents the position of player 1, and the blue LED represents the position of player 2, and the green LED represents the position of the ladder, and the yellow LED represents the position of the snake. Okay, so now moving further, this is the subcircuit of our player selector module, and this is a subcircuit of our memory module. So if we go into the child sheet of this module, we can see how we have made it. So this is the child sheet of our dice module. So in this dice module, we have used a 555 to generate high frequency pulse. This pulse triggers a Johnson counter to generate random numbers. These numbers are then passed to a decoder and outputted on the board module. Then this is our snake ladder module. So this is a snake ladder logic. So over here, we have the ladder position and the snake head position. So these positions are decoded through this logic, and then finally we can get the output in our board module. So we will describe it further in our later parts of the video. So here then we have a reset module over here. So what does the reset module do? This the reset module resets every value if triggered, forcing the game to start from point zero. This includes resetting the player's position and the turn of players, starting with player 1. And then about the decoder module. So this is our decoder module. The decoder module operates in the binary system, decoding useful information and displaying it on the board module. It uses 74151 analog decoder ICs for the decoding process. And now, oh wait, we have this is our player selector module. This player selector module uses a JK flip flop in toggle mode to switch between the two players. A debouncer circuit sends trigger pulses to the JK flip flop, ensuring stable switching. The memory module saves the player's position and sends it to the logic module to calculate the next position. Player positions are saved in D flip flops, which are triggered with every clock pulse, and when a player switches sides. And finally, this is our winning module. So whenever player 1 or player 2 reaches the winning position of 16, then the winning module gets triggered, and these are the LEDs for player 1 and player 2. If player 1 wins the game, then the LED for player 1 gets turned on, and if player 2 wins the game, then the LED for player 2 gets turned on. And finally, if either of the player 1 or player 2 wins the game, then this is a buzzer. The buzzer will indicate if any of the player wins the game, it will buzz, and thus the game will end. So this is the schematic of our board module. So there are 16 blocks in our board module. So this is one of the blocks, this is one of the blocks, this is one of the blocks. Like this, there are 16 blocks over here. Okay. So in each of these blocks, there are 4 LEDs connected with 4 resistors. The resistors is connected so that the LEDs do not get damaged when they are turned on. Okay, so now the color of the LEDs are red, blue, green, and yellow. The red LED represents the position of player 1, the blue LED represents the position of player 2, the green LED represents the ladder position, and the yellow LED represents the snake position. So in each of these blocks, we have connected the terminals from decoder module. So we have used active flow decoder over here. So at one terminal, there is an active flow decoder, and at the other terminals, there are power sources connected. So in all of these LEDs over here, there are power sources connected. So how does it actually work? So whenever the decoder is active, like if it is active for the player or the snake or the ladder, whenever it is active, then the decoder will send a low voltage over here, and since there is a there's a power source connected on the other terminal, so it will create a voltage difference between the two LEDs, and the LEDs will get turned on. Okay, so likewise, the whole board module has been designed.
Here we have the dice module with us. If we go to the child sheet, we'll get the complete schematics of it. Here we have the VCC 55 clock timer. This, and after calculating some things about it, we can find the proper capacitor and resistor value and configuration to make sure a very high level of frequency in this timer. And we have calculated it such that it provides us 20,000 frequency. So in this clock input, we are getting 20,000 frequency. And as a result, in this Johnson counter, every second this thing goes about 20,000 times it cycles through. So it is virtually impossible for a human to make a guaranteed guess in this case. And we have connected this 0, Q0, Q1, and Q2 output to that encoder D1, D2, and D3. As a result, we will get binary 0, 1, 1, 1, and 0, 1, 1, 0, and 1, 1 as an input. So this will continuously cycle through at a high speed. As a result, we'll get output over here, and this will be our binary value. If we get D1 here, we'll get 1. If we get D2, we'll get 1 0, and if we get D3, we'll get 1 1 in this binary output. We have also made sure that we add the Q3 to the reset pin so that we don't have to cycle through the unnecessary channels such as Q4, Q5, Q6, Q7, Q18, and we'll just cycle through Q0, Q1, and Q2, and Q3. And hence, we'll get this dice.
So this portion over here on the right, this is our decoder module. So how does this decoder module work? Here, the IC U29 outputs the bottom position of the ladder, while the IC U30 outputs the top position of the ladder, but both in active low logic. This signals pass through an AND gate. When all outputs are inactive, no voltage difference occurs at the LED cathode, keeping the LEDs off. However, if any decoder output becomes active, the AND gate outputs 0, creating a voltage difference that lights up the corresponding LEDs. This results in two LEDs illuminating, indicating the top and bottom positions of the ladder. Now, over here, the ICs U23 and U24 outputs the top and bottom positions of the snake respectively. These signals also pass through AND gates, which then lights up the two LEDs to indicate the snake's position. Additionally, the U21 and U22 decoder displays the player positions of player 1 and player 2 on the board module. These decoders are connected to the reset module. When triggered, they reset the IC values to 0.
Here we have the schematic for memory module. We also have incorporated the player selector memory module within the memory module. If you go to the child sheet, you can see everything here. Here we have used a JK flip-flop for our toggling purposes. This allows us to shift between two players. Here our power is continuously given, hence both J and K is getting 1. And as we know, if J and K is getting 1, our results for JK flip-flop are toggle. So whenever we get clock pulse through this circuit, we'll get the toggle here. And this is a debouncer circuit which is used primarily for smoothing out the effects of this circuit. So it will create a better edge. Now when we get 1 in this output terminal, this will go to here, and hence we'll get AB01. We have to understand that when this is 0, this will be 1, and when 1 is 1, this will be 0. So there will never be a situation where 1 1 and 0 0 occurs at the same time. Hence our Q0 and Q3 are mainly out of order. We are primarily focusing on Q1 and Q2 for our output purposes. When this is 1, we will get A as 1, so this is 0 1, hence Q1 will be activated, and this will be 2, and hence in this circuit we'll get volts as a result, because there is 1 in this place, so this 2 will get an output of 1, which will be transferred here, and hence this transistor will be open, and this will be a short circuit. So the power coming from this place will just go through here and go to the ground, and this power will not be transferred into this clock. Hence the output of the player 2 will not be selected in this memory. Now, if this is 0, this means this is 1, and as a result, we'll get Q3 as 0. And if Q3 is 0, this terminal will be open circuited, and as a result, the power going through this terminal will not go through this circuit to the ground. Instead, the current will flow through this direction and go to this clock circuit. Here, the capacitor used for smoothing purposes again, so that the edge will be much more finer, and it will just help us operate this memory better. And this is the input of player 1, player 2, and player 3, 4. And when we get the clock pulse through this branch, the clock pulse will enter all these flip-flops, and as a result, this will register our inputs of player 1. And hence, the inputs of player 1 will be set in the memory. We also have to understand that there is a reset module. If we provide power to the reset module, all this output will be 0, and hence all of our existing memory will be wiped, and this part will again be 0. But this is beyond the scope of our memory schedule for now. And when we toggle this again, when this part becomes 1 and this part becomes 0, we will get Q2. And if Q2 is 1, that means this circuit will be shorted, and hence the current will go through this and come to this ground. Hence, result, this register will not get any clock pulse, and they will not trigger. Instead of that, P2 will trigger. As a result, the output terminal of this 2 will be 0 when this is 0. Hence, this is 1. Hence, we get this 1 output, 0 output here, and this will be open circuited. As a result, the current going through this resistor will go through this branch instead of this. And as a result of going to this branch, the clock pulse will be triggered. As a result, the player value of this P1, P2, P3, 4 will be registered in this specific portion, which is used for player 2. We also have the selector module here. This selector module E1 and E2 will be depending upon the entrance of this. The selector module can use this Gmux to get different values. This is for player 1. This is also for player 1. This is also for player 1. This is also for player 1. This is the 4-bit of player 1 that we'll use, and this is the 4-bit of player 2. When we'll provide in 1, the selector in 2 will get the results for P1, P11, P12, P13, and P14 at this P1, 2, 3, 4. And when this is in 2, we'll get the result for P21, P22, P23, and P24 as the result of this Gmux. And as a result, this is how this memory module and the selector module works.
The parent sheet of our snake ladder module, it takes the inputs of 2 players. Here, 4 input for player 1 and 4 for player 2. Then we have dice input here and player selector input from memory in 1 for player 1 and in 2 for player 2. We also have inputs of ladder starting position, ladder ending, ladder length, and snake head position, snake length position. These are the inputs we're getting from these logic states over here. And here is the output of our snake ladder module. The output after all the operation is done, we are getting output for new position output for player 1 and new position output for player 2. So let's see the child sheet of our snake ladder module. At first, we have a multiplexer which selects data based on the information from the memory module. It determines either in 1 or in 2 will pass through. The selected input is then processed by an adder, and the dice value is added, and then we get the new position of the player. But the new position of the player might get ladder or snake. We need to compare the ladder position and snake position via two comparators. If the comparison matches, then the information will pass through this multiplexer. Then the multiplexer will operate thoroughly. And if it is a snake, then the snake terminal will get the signal. And if it's a ladder and snake both, then ladder will get the priority. And this OR gate is setting the priority over here. And also, ladder terminal will be on. So if snake terminal is on, then the next operation will be over here. This XOR gate will work as NOT gate, and it will invert the snake length information. And we will get the information of ladder length as exact. And this multiplexer will also be selected by this snake terminal and ladder terminal over here. So if there is ladder signal on, then exact ladder length information will pass through this multiplexer. And if the snake terminal is on, then the inverted ladder snake information will pass through. And also the carry in of this adder will be determined by this snake terminal. So for snake, this adder will work as a subtractor, and for ladder, it will work as adder. And this will be the new position of our player. But we used this extra adder to solve the overflow issue of our board. If our player is in 15 or 14 position, then this adder will work. Normally, the real value of the summation will pass through, and this configuration over here won't work perfectly as the C1 terminal won't get any signal. But once the carry out will be here, the overflow will start happening, then the C1 terminal will get on, and it will let the inverted dice value pass through this adder, and also this adder will start working as a subtractor, and it will hold the position in new player position in the board. And so this will be our output of our snake ladder module. This is the output.
Schematic of our winning module. Whenever a player reaches the position 16 of the board module, the player wins the game. However, there should be a method to identify which player has won the game, and there should be an indication that the game has concluded. So for this, we have used this winning module. So at this terminal of the winning module, it indicates that the player 1 has reached the position 16, and this terminal indicates that the player 2 has reached the position 16. So we have used an active low decoder over here. So that means whenever the player 1 reaches the position 16, it will send the signal 0 over here, and the signal 0 will go through the NOT gate, and through this NOT gate, there will be a voltage difference between the terminals of this LED for player 1. So if the player 1 wins the game, then the red LED for player 1 will be turned on because of the voltage difference. And then again, the signal 1 will go to this XOR gate, and the output of the XOR gate will again be 1. And this 1 output will go to this NOT gate, and this NOT gate will turn it into an output of 0. Now, in case of this buzzer, at one terminal of the buzzer, there is a power source connected, and if the other terminal of the buzzer gives an input of 0 over here, then the buzzer will get turned on, and it will indicate that the game has concluded, and the player 1 has won. Similarly, the winning of the player 2 can be explained.
Our every module are here, and the integration between all the modules are going to be described now. So this is our board module, and in board module, the decoder module gives the output. The output from decoder module goes in the board module, and the input of decoder module comes from our memory module. And right now, the memory module is giving 0000 output input that is showing in this active low decoder. And afterwards, so the player 1 and player 2 is turned on over here. And this is our snake, and this is the ladder LED. And from memory, we are getting that 000 position of player. And in the memory, there is the input that goes from our snake ladder module. And in snake ladder module, the output goes to our memory module, and the input is from our player current position of in board, and the dice value after roll. And then all the operation happens in snake ladder module, giving our new position of the players. And then the new position of the player goes in this terminal, but it does not pass through the memory module. When the clock pulse of this bouncer mode of this bouncer circuit goes in, then only when through this multiplexer, the information passes through this memory module, and the new position of the player then is detected by this decoder module, and then the decoder module again gives output to this board module. So when we are actually rolling our dice, then we're getting 3. And then when we are selecting our player selecting, then this is connected with our bouncer circuit. And when we are pressing it, then the memory is getting clock pulses. So the player 1 shifts with the operation. Now the player is in a 3 position. So that's how the entire game was integrated. Let's test our snake ladder game. This is the board model of our snake ladder game. This red LED is for player 1, blue for player 2, and yellow for snake, and green for ladder. Let's roll the dice. Okay, so according to our configuration, the first turn is of player 1. So when we will select the player selector, player 1 should move forward, means red LED. Okay, did. Now is the turn of player 2. Okay, so the roll dice operation is working perfectly. Let's see if our ladder operation and snake operation is working perfectly or not. This is the ladder operation, ladder starting point. We need 2 to get the ladder for player 2, but it's the turn of player 1. So let's use player selector. Okay, so player 1 got the ladder as player 1 needed 3. So let's check the snake operation with player 2. So we can use 3. It won't affect. Okay, let's roll the dice. Let's use 1. 1 is better. Okay, we got 1. So it's the turn of player 1. So red LED moved. Now it's the turn of player 2. So the snake operation should work. Okay, it did. So the snake operation and ladder operation is working perfectly. Let's see if the winning module is working perfectly or not. So let's see who wins. Let's roll dice. Is the player 1, and then it's of player 2. Okay, so it's player 2. Okay, so player 1 is won. So let's reset the game. Okay, so now we can play again as we used to reset game. So we can start the game and play again. So we tested our game.